we defined acceleration as the rate of change of velocity, right? Remember, velocity was the rate of change of position. Not the change in position, but rather how quickly the position changes. Acceleration is the rate of change of velocity. Not the velocity, but how quickly the velocity changes. You can have a high velocity even if you have a low acceleration. Or you can have a high acceleration even if you have a low velocity. The two aren't related. Acceleration is related to the change in velocity, not to the absolute velocity. Now, the symbol for acceleration we said was A, of course, and it had a little half arrow over top of it, which meant that acceleration is a vector. Good. And what were the units that we usually use for acceleration? Meters per second squared. In fact, we're not going to say usually used for acceleration. We're going to say always used for acceleration. When we were doing constant velocity or uniform motion, v is equal to delta d over delta t, we said the standard units were meters and seconds in meters per second. But we could use other units as well, like kilometers and hours and so. Now that we're doing acceleration, we got to do meters and seconds in meters per second in meters per second squared, right? So going forward, unless it's just a straightforward v is equal to delta d over delta t problem, you're going to use the standard units, meters, seconds, meters per second squared for this. We saw a couple examples of both positive accelerations and negative accelerations yesterday. When was acceleration a positive value? I'll give you a hint. There were two situations where acceleration was a positive value. Yep. Good. If it's slowing down in the negative direction, an example of that would be if I drop something and it hits the ground. As it collides with the ground, not when it falls, right? When it's falling, it's speeding up. But as it collides with the ground, it slows down. But it's still moving downward. As it moves downward in the negative direction, but yet slows down, that's a positive acceleration. Right? What's the other situation where we have a positive acceleration? Good, when we speed up in the positive direction. So in other words, if a rocket was taking off and going upwards, and it's speeding up as it goes upwards, then that's a positive acceleration. Now, on the other side of it, when do we have a negative acceleration? The opposite of that, right? Sorry? Good, when we're speeding up in the negative direction. So if we talk about that board marker again, falling, we're talking about the acceleration downward before it hits the ground. As it hits the ground, it slows down in the negative direction. That's a positive acceleration. But as it falls and speeds up in the negative direction, that's a negative acceleration. What was the other situation where we had a negative acceleration? What does it say?
Slowing down.
Good, slowing down in the positive direction. So the example of that would be the board marker or whatever going up into the air, but slowing down as it's going up into the air. Good. Pay attention to that, right? Pay attention to that. A lot of times when we see that, it's the result of a calculation. We've calculated the acceleration, and the math will tell us whether it's positive or negative. But man, it's always a nice little check, right? If we get an answer that's negative, and you stop and take a step back from it for a second and say, oh wait, that should be a positive number because it's slowing down in the negative direction. Sometimes it tells us that we've made a mistake, right? Or sometimes it confirms that we've done the right thing. The other thing is sometimes we just have to know. Like, problem might say, the acceleration of the object is, the magnitude of the acceleration is 2.0 meters per second, and you've got to know whether to plug it in or sub it in as a positive or a negative value. Good. Last little thing on this page here. Do you guys remember what the acceleration was of an object as it falls, or the acceleration of an object as it rises up into the air? On Earth, that is. Not on the moon. We saw that video yesterday. On the moon, it's quite a bit lower, right? About 1/6 of what it is on Earth. But on Earth, in the absence of anything but gravity, what's the acceleration going to be? Yep, but what's the value going to be? What's the value of it going to be? Good, negative 9.81 meters per second squared. Even if it rises, right? How is it negative when it's rising up into the air under the influence of gravity? What's happening to it as it rises up into the air? It slows down in the positive direction. That's a negative acceleration. So we're always going to make, in the context of these questions, we're always going to make A for gravity negative 9.81. Now, if there's Air resistance, that throws a wrench into things, right? The acceleration isn't negative 9.81, but normally we don't encounter that in Physics 20, where we have to deal with air resistance. Okay, the analysis of that is actually quite a bit more complicated. You have to do some calculus, which none of you guys have learned yet. Reason being, gravity is a constant value as something falls, but air resistance changes depending upon the speed and depending upon the shape of something as well. As something falls, it speeds up and speeds up, but the value of air resistance keeps getting bigger and bigger and bigger. So it's not just a matter of combining gravity and air resistance simply. You got to do it much more complicated way. So that's beyond Physics 20. Yesterday we learned 5 new equations. 5 new equations. We had one. It was V is equal to delta D over delta T. We called that our group. Yeah, we called that our group A equation. We're still going to call that our group A equation. We're still going to use that from time to time. But we're going to use that, our group A, only when we have constant or average speed or velocity. Group A, constant or average speed or velocity. So whenever you see a question going forward here, I want you to look at it and say, is this constant velocity or is this acceleration? If it's constant velocity, use group A. If it's acceleration, you use group B. Lots of different equations here. Yesterday we did one example. Somebody, I think, if I remember right, gave me an equation that did not solve for the variable I was looking for in that example. Was that the case in this class? Yeah. That's okay. That's always okay. If you write down your givens and then you use an equation and you end up solving for displacement when you're looking for acceleration, that's not wrong, as long as you don't stop there. Okay? You solve for something you're not looking for. I'm not going to mark that wrong. Okay, just keep going until you solve for what you're actually looking for. Whenever you have acceleration, you can try any of these 5 equations. You cannot go wrong as long as you use them properly. You can't go wrong. Okay, the worst case scenario is you can end up with 2 unknowns, and you're like, I can't solve this because I have too many unknowns. Or you're going to solve for something you're not looking for. Okay? In either case, what do? Try another one. Just try another one, right? If I tried this equation, I thought, oh, that's going to work for me, and it didn't. All right, try this one. If that doesn't work, then try this one. If that doesn't work, try this one. If that doesn't work, well, that one's got to work then, because something has got to work. And the beauty of this is you're not going to get the wrong answer. As long as you choose from the right group of equations, you're not going to get the wrong answer unless you actually do something wrong. Okay? All right. We had one question for homework yesterday. It was worksheet number 4, question number 1. We'll go over that, and then we'll take a look at another example here. Worksheet number 4, question number 1. It says, a car accelerates from rest to 10 meters per second in 3.5 seconds. Calculate the car's acceleration. Here's what I want you to think first, going forward now that we have 6 equations. A lot of people say, what do we do first? Write down the givens, right? Now, you know what? I don't actually think that's the first thing we should do. That's important. Givens are really important, but it's not the most important thing. At this point, I want you to recognize what's happening in the situation and then write down my givens. What's happening in this situation? This car is accelerating, right? This car is accelerating. It's speeding up from rest, which is 0 meters per second, to 10 meters per second in a certain amount of time. What kind of a problem is this? Is this group A or group B? Is it? This is group B. We're allowed to use those 5 equations that we learned yesterday. We're not allowed to use the blue one. Okay, if you try one of the red ones here, and you use them properly, you can't go wrong. If you try the blue one, you'll get the wrong answer. So go with one of the red ones, and hopefully it works out. If it doesn't, just try another one, that's all. Let's write down some givens first. This is what you should always do right after we look at what's happening in the problem. Something's 10 meters per second. What is that? Velocity? What velocity is it going to be? Yeah, that's going to be VF. Good. Do we know what VI is? Yeah, VI is 0 meters per second. My time here is 3.50 seconds. So we write this down, right? We write this down. We always show these givens. And then we show the equation. Sorry, what are we looking for? A, VI, VF, T. A, by the way, we don't have it, but we'll kind of think of it as we have it when we look at our equations. Okay, so think A, VI, VF, and T. A, VI, VF, and T. Which of those 5 group B equations do you think is going to fit best? Art? D is equal to VIT plus 1 half AT squared? Okay, Aaron, let's try that one. D is equal to VIT plus 1 half AT squared. So D, we don't know, that's fine. VI is 0. 0 times time is 0 plus 1 half of A times T squared, 3.5 squared. Is this wrong? Absolutely not. Well, what's my problem with this equation? Yeah. Yeah, I got too many unknowns. I don't know what D is. I don't know what A is. That's fine. Okay, I recognize that and say, well, it wasn't the right one. Right? Didn't give me the wrong answer, and it never will, as long as you're choosing from the right group. Now, Aaron didn't really say that. Which one did you say, Aaron?
A equals delta T.
Yeah, A is equal to delta V over delta T. All right, let's try that one. We tried the first one, didn't work. Now we're going to try the second one. A is equal to delta V over delta T. Delta V is VF minus VI over T. This one's going to work, right? 10 divided by 3.5 is 2.86. And the units for that would be meters per second squared. That's my answer. Hey, somebody might have tried the one that I tried first, didn't work. Tried another one, didn't work. Tried another one, didn't work. Sooner or later, like, you're going to have to try this one, right? It's going to work. Now, as we get more and more comfortable with this and better at it, you tend to recognize more quickly which one is the one that fits the givens. And you don't need to try 3 or 4 or 5 different equations, right? But in the end, if you do try 3 or 4 or 5, that's okay. As long as you don't try V equals D over T, because that one's only valid for constant or average. And that's not what we got here. All right? Okay, let's take a look at example number 2. Sorry, it's actually example number 9, I guess. Example number 9 in your notes here. All right, so this one relates to example number 8. So I'm going to write down my givens, actually, for example number 8 as well, and then go to number 9. In number 8, we had a VI of 10 meters per second. In number 8, it speeds up to a velocity of 25, so we said VF was 25 meters per second. My time interval in number 8 was 6.0 seconds. We were looking for the acceleration. Now, there is actually one more thing. These were my givens for question number 8, right? Example number 8. There is one more given that we actually have now for question number 9. What is it? Let's look back to number 8. I just wrote down that I have VI, VF, and T. VI, VF, and T. There is one more thing that I have now for question number 9. Marcello, what is it? Yeah, good. I have acceleration. I solved for that in question number 8, right? So let's write that down as well. Sorry, we're not looking for acceleration there. We've got it, and it was 2.5 meters per second squared. That's not given to us in the question, but we solved for it already in question number 8. We're looking for the displacement. Okay, I should have actually thought about the question first before I did this. Determine whether it's group A or group B. What is it? A or B? Mia, what is this? Is it group A problem or group B problem? Yeah, because it involves acceleration, right? Speeding up or slowing down. In this case, speeding up, but slowing down would work there too. If it's a group B equation, knowing VI, VF, T, A, looking for D, which of these 5 group B equations do you want to try? Ryan, you have a preference here? Which one do you want to try? VI, we have VI, we have VF, we have A, we have T, we're looking for D. Let me give you a hint here, okay? Set your mind at ease here. Okay? Relieve your anxiety. As long as you pick from the right group of equations, and this is an acceleration problem, you can't give me a wrong answer for this. Okay? So, which one do you want to try first? D is equal to VFT. Okay, let's try that. D is equal to VFT minus 1/2 AT squared. VF is 25. T is 6 minus 1/2 of 2.5 times 6.0 squared. Look, that's going to work, right? Good. By the way, it's not our only option. There's a few options here, but that absolutely works. All right, let's calculate this now. At this point, I'm going to do this in stages, okay? It's not going to be long before I start showing you how to use brackets on the calculator, but right now we're just going to focus on doing little bits at a time. So I'm going to calculate that first number, 25 times 6. That gives me a value of 150. So let's write that down. Subtract. And then I'm going to say for the second bit, I'm going to say 0.5 times 2.5 times 6, and then the squared button right there. 0.5 times 2.5 times 6 squared. That gives me a value of 45. So it's 150 minus 45. Now, if you have an 84 calculator, you can do this. If you have an 83, an 83 plus, you're going to have to just type in the number 150. But with an 84, you can go back and select that number, and then go back and select that number. What do you got? Oh, you should be able to do that, I think. No? All right. The answer is 105. In the end, worst case scenario, you just got to type it in again, right? Gives me 105. By the way, that should actually be 2 digits. 2 digits, right? Because if you look back to question number 8, my original data was 2 digits, right? So how do we round 105 to 2 digits? That's the third digit. The third digit is 5, so the second digit rounds up, right? So it becomes 110. Oh, but 110 isn't 2 digits. It's still 3 digits, right? So we're going to call that 1.1 times 10 to the 2, right? We move the decimal place over 2 places. 1.1 times 10 to the 2 meters. Let me show you a little trick on the calculator for that one too. Look at this. So how did I get 105? Watch this. I'm gonna go into mode in my calculator. I'm gonna go over to scientific. Press enter. Go back there. My answer is 105. I'm gonna multiply that by 1. Why am I gonna multiply that by 1? So I get the same answer, right? Now it gives me 1.05 times 10 to the 2, which I have to round to 1.1 times 10 to the 2 in order to get 2 digits. Make sense? Some people like to leave their mode in scientific notation. Whatever. I don't. I like to leave it in standard notation, but whatever you want. Okay, so Ryan gave me this one. We didn't have to do it this way. Does anybody else think another one of those group B equations? Jack? D is equal to VI plus VF over 2. Okay, let's try that. VI is 10. VF is 25. T is 6.0. This looks like it's going to work, yeah. Whoops, this should be a 2, shouldn't it? Times 6.0. So 10 plus 25 is 35. 35 divided by 2 is 17.5. 17.5 times 6 is 105. Or we're going to say 1.1 times 10 to the 2. Man, it's not a coincidence that you get the same answer, right? If both of those equations will give me an answer, if they give me an answer, then it has to be the same one, unless I've made some silly mistake, like putting a negative where it shouldn't have been, or so on. Now, I'm not going to say that one way is better than another. Okay, both ways are absolutely correct. The one advantage to Jack's way here is that it doesn't use your answer from number 8. That makes sense? So if we do it this way, if the answer in number 8 was wrong, then the answer to number 9 is wrong, right? Now, having said that, Ryan, okay, you know from the quiz that you guys wrote this morning that I'd still give you marks for that. So it's not a huge deal. But again, a small advantage of this is that it doesn't depend upon question number 8. Get it? All right. Let's take a look at, for you guys here now, let's say right now you work on worksheet number 4, questions 2 to 6. 2 to 6 and number 4. Let's have a look at another example, all right? Example number 11 says a ball rolling down a hill accelerates at a rate of 3.0 meters per second squared. If it initially moves at 5.0 meters per second, how far is it going to travel in 10 seconds? Is this a group A or is this a group B problem, Sam? Pardon me? Yeah, it's a group B problem, right? Because it's accelerating, right? Speeding up as it goes down the hill. If it's a group B problem, we know we're going to use those 5 equations that we learned yesterday, not V equals D over T. That's the only one we can't use, right? All the other ones that we've learned we can if they fit the givens here. Let's write down some givens here. Something's 3.0 meters per second squared. What is that? What is it? Yeah, that's the acceleration. Now, some people in this question will make A negative 3.0 because it's accelerating down the hill, right? I would suggest in a case like this, since everything is down the hill, just make down the hill positive. Does that make sense? And then everything that we've got is a positive value. If you make it negative, that's okay. You're just going to end up with a negative displacement instead of a positive displacement. It's not a big deal. What else do we got here? 5.0 meters per second. What is that? That's going to be VI, the initial velocity. Good. Now, if I had to define down the hill as negative, then this would be negative 5 meters per second rather than positive 5, right? We've got delta T is 10 seconds, and we're looking for delta D, how far it's going to go, the displacement. Actually, technically, we're only looking for the speed, right? Or sorry, for the distance, right? How far is it going to go? Technically. But in the end, if I solve for the displacement, it's not changing direction, is it? It's going downhill the whole time, so the distance and displacement will be the same number, right? So let's just get displacement here. What do you want to do? We got 5 equations that we're allowed to do. A, VI, T, and D. A, VI, T, and D. Which one do you want to try here? The third one? This one? Yeah, sure. Let's try that one. D is equal to VIT plus 1/2 AT squared. That one is going to work for us. And if we recognize that right away, then saves us some work, right? But if we don't, that's okay. We try one and see if it works. Sometimes we try one, get something that we're not looking for, and then we use that something that we just found in another equation, right? Sometimes, even though we use an equation that's not going to work for us right away, it's still helpful because we end up getting another given out of it. This one's going to get us the answer right away, though. 5.0 meters per second times a time of 10 seconds plus 1/2 of 3.0 times t squared, 10 squared. 5 times 10 is 50. Do that on your calculator or in your head, right? 5 times 10 is 50. Plus 10 squared is 100. 300 times 1/2 is 150. Do it in separate stages here, right? 50 plus 150 is 200. But how many digits does it need to be? 2. So we got to make this 2.0. Scientific notation is always number, decimal number, times 10 to the what? Yeah, 2.0 times 10 to the 2 meters. Move the decimal place over 2 places. Good? All right, it's 9:44. We'll give you another about 6 minutes to keep working here. And then I'll do one more example before we wrap it up for the day. At this point, I would say, guys, even if you get to question number 6, keep moving. Just keep working through the worksheet here. And then I'll decide, based on how far you guys get, how much we assign for homework. Okay. One more example here, and then we'll wrap it up for the day. Question number 10. Example number 10 says, a rock falls from a height of 50 meters above the ground. What's its speed when it strikes the ground? Is this a Group A problem or a Group B problem? It's definitely Group B because it's accelerating, right? This rock accelerates at a rate of negative 9.81. I'm going to write that down as a given, actually, right now. A is negative 9.81 meters per second squared. How come we're making it negative 9.81 rather than just 9.81? It accelerates downward. It speeds up in the negative or downward direction. Good. What else we got here? Falls from a height of 50 meters. So it falls 50 meters. What is that going to be? We're going to make that the displacement, right? Displacement is 50 meters, right? There's something wrong with what I just did. Small thing, Aaron. Yeah, it's going to be negative 50 meters, right? Because the displacement is downward. We end up below where we started, right? If A is negative 9.81, then delta D has to be negative 50 to be consistent with that. I should have said a rock is dropped because I meant to make VI 0 meters per second. Now, the way that this is worded, it doesn't actually tell us that VI is 0 meters per second. If it's dropped, VI is 0, right? If it's thrown, VI is not 0. If it just falls from this height, it's not really telling us. Okay, it was meant to be, though, starts at rest. We're looking for VF, the speed that it hits the ground. Which equation you want to use? Which equation do you want to use? Yeah, any of these Group B equations are valid, right? Let's try that that middle one, bottom. That's the one you want to try first, so let's give it a whirl here. VF squared is equal to VI squared plus 2A times delta D. If we rearrange this, we're solving for VF, so that's about the easiest variable in this equation to rearrange for. Get rid of what's not attached. Well, there's nothing not attached to the VF, right? Get rid of what is attached. What's attached? Squared. How do you get rid of it, Kim? Square root it. So we're going to say VF is equal to the square root of VI squared plus 2A times delta D. Now, this is 0, isn't it, VI? If VI is 0, what's 0 squared? 0. So I'm just going to cross that out. 0, right? I don't need to put that into my calculator. VF is going to be equal to the square root of 2 times negative 9.81 times negative 50. Now, watch me on the calculator here. We're going to say, don't worry about the square root sign right now. Hey, do one thing at a time. 2 times negative 9.81 times negative 50. If you get a negative number there, you know you've done something wrong. How come? Yep. Because you can't square root a negative number, right? And math, whether you like it or not, is elegant. Like math will always work. If we do what we're supposed to do, the signs will always work. So this has got to come out to be a positive number under the square root sign. Don't forget to square root it, though. We just found what's inside the square root sign. Let's second function square root this, and then second function answer. You can do that no matter what version of the calculator you have. Okay? Second function answer. 31.3. Our final speed is 31 meters per second. Now that's our final speed. What would our final velocity be? 31 meters per second down. Right? We weren't looking for velocity, we were looking for speed. But if we were looking for velocity, we could have found this and then just added the down to it. Yeah.
Is it okay to leave the square on the final velocity?
Until the end? Yeah, that's fine. Yeah, so you're subbing in your numbers and then rearranging. That's fine. Yeah, it doesn't really matter. Good.